In this video, we are going to be talking about the second and last of our special types of, or special cases of discrete probability distributions, right? And that is with the Poisson distribution, right? So the Poisson distribution and the binomial distribution, they have some similarities, although they are distinct, right? So one, right, they're similar in that the Poisson random variable is a count of the number of successes right? So just like the binomial random variable, the Poisson, I probably should just not stand right in front of that, should I, after I just wrote it. But again, just like with the binomial random variable, our Poisson random variable is a count of the number of successes. Right? The difference comes in that where for a binomial, right, we are looking at the number of successes over a set number of trials. Right? For the Poisson, we are looking at the number of successes over some fixed interval of time or space. All right, so we might be trying to figure out, what's the probability that 3 airplanes go down in a month, all right? That's something that you might use the Poisson distribution for, all right? So you're looking at the number of successes. Again, in this case, it's a plane crash. It does not have to be something positive, although it can be. I think I make most of mine something negative. But they can be positive things as well, all right? And then we're looking at, so the number of successes, a success being a plane crash, right? Over an interval of time or space, that time being a month in that example, all right? So we're gonna have some fixed unit of time. Usually it's gonna be time, it can be space, so kind of, well, it can be space. All right, we'll just leave it at that. All right, I think I once did an example of the number of kind of power outages per mile, like for however many miles of power line that a company did. All right, so that could be where you might use space instead of time. All right, but more commonly, it's going to be time. All right, but now let's actually start talking about the distribution itself. All right, so just like with the Poisson, we're going to have some conditions. All right, so these are conditions for a Poisson random variable. All right, and we only have 2 for the Poisson. All right, the first one is that successes occur one at a time. All right, so we cannot have successes happening concurrently, right? And second, the occurrence of a success in any interval is independent of the occurrence of a success in any other interval. All right, so that's a very long way of saying successes are independent of each other. All right, they could have cut out most of that. But that is essentially just kind of a standard, right, independence statement. All right, so successes occur one at a time, and successes are independent of one another. Right, so if we have a success in one period or interval, it does not change the probability of having a success in another interval. All right, so those are our conditions. Now we can move on to the probability distribution function. So this is our Poisson probability distribution function. All right, I'll go ahead and warn you as I'm writing this up. It looks worse than it is. All right, so the probability that x equals, actually I'm going to move that down a little bit. All right, so equals e to the negative lambda times lambda raised to the x over the factorial of x. All right, so again, this one looks a little rough, but it's really not that bad. All right, E is just a mathematical constant. All right, so you've got a button on your calculator to put E in there. All right, and it's going to go ahead and raise. It's going to be E raised to the whatever you type in there. All right. It's usually the secondary function on your natural log button, so that's the LN button on your calculator. For this Texas Instrument here, right? It's the third one from the top, right, on this far left row. If you have a Casio or something, it's somewhere on there. Just look for that natural log button. It's going to be around the log button as well. All right, but that's all E is. All right, it's just a mathematical constant. All right, lambda. All right, lambda is the average number of successes for a given interval. All right, so an interval of time or space. All right, and that is something that is important to note, because if we change the interval we're talking about, we're going to have to change lambda. All right, so if we go from talking about the number of successes over an hour to the number of successes for a day, right, then your lambda is going to be two different things. All right, and you need to adjust that or you're going to get the wrong answer. All right, and then x is just our number of successes, right? And that's going to come from whatever probability we're looking for. If we're looking for the probability x equals 5, then x is 5. If we're looking for the probability that x equals 20, then x is 20, so on and so forth. All right. One other thing before we actually look at an example. When you go to put negative lambda, all right, raise e to the negative lambda, all right, there are two buttons on your calculator that look very similar. All right, you've got the minus button, right, the subtraction button, that's going to be right there with all your other kind of operators, time or functions or whatever you call them. You know, your multiplication, division, addition, so on and so, well, not so on and so forth. Those are the three other than subtraction. But do not use the subtraction button, all right? Because if you do, for many types of calculators, you're going to get an error, right? Because you can't. Well, they're just not programmed that way, right? So don't use that. You also have a button that should swap the sign, right, or a negative button, right? Here for this calculator, it's right up here with all the numbers, right, and it's this bottom right button right there, all right. So across from the 0, right? Depending on what your calculator or the type you have, right? It might be different. Just some common symbols. So on my Texas Instrument, that's what the button looks like, right? It's a kind of a dash in brackets, right? Some of them will have something that looks something like this, all right? Plus, minus, switching around, so you can change, excuse me, so you can change the sign of what you're working with, right? But you need to use that instead of the subtraction button because it will give you an error, right? Or at least it often will, depending on the calculator. All right. So, so then before we do an actual example, the expected value for a Poisson random variable, all right, this one's pretty easy. It's lambda, all right. The expected value is the mean, right? Another word for a mean is an average, right? And so if lambda is the average number of successes, the average number of our random variable happening for a given interval, right? Then the expected value is also lambda. We would expect the average to be the answer, right? And the variance for a Poisson random variable is also quite easy. It is also lambda, all right? So probably won't surprise you. Probably won't ask you too many questions about, or ask you to calculate the expected value and the variance for a Poisson random variable, right? But it is lambda, all right? That's not to say that I can't ask you about it. I might, but it would basically be free points as long as you had lambda, or you just knew that the expected value was equal to lambda. All right, so we'll go ahead and actually look at an example of this. All right, let's say, so a drive-through attendant, I don't know if I'm spelling that right. That's okay. Noticed there was an average of 2.7 customers every 10 minutes. All right, and we're going to assume that these customers came one at a time. All right, none of them came at the same time. All right, so we can meet our conditions in that. Although perhaps not necessarily true, but we're going to pretend like the second condition is met and that the successes are they are independent of one another, right? So we can assume our assumptions are met. All right, so when we go to answer a question like this, well, one, we don't have a question to answer. I should probably give us one, shouldn't I? All right, so let's just start with a simple one, right? What is the probability that there are no customers in a 10-minute interval? All right, so that's kind of the starting information, and then also our question. All right, so looking at this, all right, there's a couple of things that we might notice. One is that we've got an average of 2.7 customers, right? Well, that's kind of pointing us to one, what lambda is, and then two, also telling us what our successes are. And then the actual question probably clears that up even more, right? So our random variable, right, our Poisson random variable is the number of customers at the drive-through, right? And we have an average of 2.7 every 10 minutes. All right, and so that's telling me that's lambda. All right, that's the lambda for a 10-minute interval. All right, luckily for us, right, we're being asked for a probability about this random variable in a 10-minute interval. All right, so let's go ahead. We're going to kind of erase this. We should all have that done by now. And we will pop up our probability distribution function once again. So just as a reminder, even though we just looked at it, right, e to the negative lambda, lambda to the x, x to the, and then divided by the factorial of x. All right, and then also, I think I forgot, I didn't even mention this. All right, the factorial, in case anybody forgot, that's going to be in your probability menu. Right, it's going to be if you actually have to go into a menu like on the Texas Instruments, it will be in the same place. So the same way you navigate to that combinations function, right? It's going to be the same way you navigate to the factorial. It's just going to be, I think, for mine, it's right below it. For the Casio or something like that, it's going to be a secondary function of a button that's near your combinations button, right? And it'll probably look exactly like that, x factorial. All right, so we know that we're looking for the probability x equals 0, right? That is the probability we're looking for, and we're looking for it over a period of 10 minutes, right? And we luckily know the average number of customers at the drive-thru for a 10-minute period, right? And that is 2.7, right? We know that because we were told that in the problem, right? So lambda equals 2.7, right? E is a mathematical constant, and x is going to come from this statement right here. So x equals 0, well then x equals 0, right? And so once we've got that, right, we're just going to fill this in. So e to the negative lambda, lambda is 2.7, times lambda to the x, lambda is 2.7, x is 0, so 2.7 raised to the 0th. And then we're going to divide it by the factorial of 0. All right, so a couple of things. So we remember that that anything raised to the 0th is going to be 1, right? Also, just as a rule, 0 factorial, or the factorial of 0, also equals 1. All right. So if you punch that into your calculator, 0 factorial, you're going to get 1. Just in case anybody was saying, hey, we're dividing by 0, that's not possible. The factorial of 0 is equal to 1. All right, but again, once we punch all of this into our calculators, we're going to get a probability of 0.067. All right, so the probability that there are no customers in a 10-minute period is 0.067. All right, let's do a slightly harder one now. All right, let's say this time, all right, so what is the probability that there are at least 3 customers in 10 minutes. All right, so once again, we're talking about a time span of 10 minutes, all right, and so our lambda stays the same, it's still 2.7. Right, but this does introduce some interesting problems. Right, one probably tells me why I used at least 3 in my binomial problem, because I had to make that one up on the spot. and I guess I was just thinking of this one that I had written down earlier. All right, but what we're doing, it's going to be the exact same, essentially, probability statement, right? At least 3, at least is telling us that 3 is included, right? And so at least is going to tell us greater than or equal to, right? So x greater than or equal to 3, right? So how are we going to go about solving this, right? Well, we know that the probabilities, or these discrete probabilities, are additive, right? That is a property of a discrete probability distribution, right? And the Poisson distribution is a discrete probability distribution, right? So how would we solve this, right? Would we say, all right, well, it's everything at 3 and up, all right? So probability x equals 3 plus the probability x equals 4 plus the probability x equals 5, right? The problem with that is, where do we stop? All right? Unlike with the binomial that has a cap, right, an upper limit because there's a set number of trials, right? There is no upper limit for our Poisson random variable, all right? Theoretically, all right, our Poisson random variable could continue to go on to infinity, right? We can't calculate all of those probabilities. Right, so we're going to have to use something that we learned in chapter 5. All right, and that is the kind of the rule. Right, it is how to find, all right, how to calculate the probability of the complement of an event. All right, and that's what we're going to be doing here as well. All right, so because we can't solve this in the kind of traditional fashion, right, we can't do x equals 3 plus x equals 4 plus x equals 5, so on and so forth. All right, we're going to have to do something else. All right, so I'm just going to rewrite this down here. So the probability that x equals 3, all right, is equal to 1 minus the probability that x is less than 3. All right, this is everything that's 3 and higher, right? This is everything that is 2 and lower, right? 2, 1, and 0. That's really all this is. All right. So instead of calculating an infinite number of probabilities to try to find the answer for this, right, which is not even possible, right? Instead, we are finding 3 probabilities, adding those up, and subtracting them from 1. All right, so once again, all right, probability x equals, oh wait, no, we already did that one. X is less than or equal to 3 equals 1 minus the probability x is less than 3, right? So probability x equals 0 plus probability x equals 1 plus the probability x equals 2, all right? That's what we are going to find. All right, so we would just find all of these. One, if this was actually a homework, right, we've already found probability x equals 0, so we just pop that in there. I'm going to set it up just so we can see it again. All right, so e to the negative lambda. All right, lambda is still 2.7 times 2.7 raised to the lambda, or 2.7 raised to the 0th over the factorial of 0, right? And then just like with the binomial density or distribution function, right? The only thing we're changing from probability to probability is x, right? If we're calculating it for a specific interval, right? That's the only thing that's going to change, all right? So the probability x equals 1 is just going to be e to the negative 2.7 times 2.7 raised to the first over the factorial of 1, right? And then finally we're going to add e to the negative 2.7, 2.7 squared divided by the factorial of 2. All right, so we get 0.067 for the probability that x equals 0, then 0.181 for the probability that x equals 1, and 0.245 for the probability that x equals 2. All right, so once we've got that all together, did I write that out? No, I didn't, but I can backtrack. All right, we're going to have 1 minus 0.493. All right, so that's going to give us a final probability of 0.507. All right, and so that's how we would calculate one of these problems. All right, so again, remember, if we're all right, just a note. I originally wrote this as less than or equal. That it's not the problem we were doing. Right? It should have been greater than or equal to 3. All right. So I want to make sure everybody take a look at that, see if you wrote it down correctly, even though I didn't, and if you just wrote down what I did, because that's probably what most of you did, because I'm the teacher, then erase it and put greater than or equal to. All right. That'll give us the correct value. All right, but that is how we would solve that. One last thing that we need to talk about with the Poisson, and then we will be done with chapter 4. All right, let's say we were asked, all right, what is the probability that there are between 14 and 17 customers inclusive in an hour. All right, so a couple of things here. All right, let's just start by setting up our probability statement. All right, so what is the probability that we're looking for? All right, so 14 and 17 customers, so between 14 and 17. All right, so these are going to be out on our edges. All right, so we got our 14 and 17. All right, then when we're looking for what inequality statement or inequality symbol we need, right? They're going to both be less than. That's the standard, all right? But then we also have this inclusive. All right, so inclusive is saying that we're going to include these endpoints. All right, so 14 and 17 are included. All right, and so when we have inclusive, right, we need to use less than or equal to. So 14 less than or equal to x, less than or equal to 17. All right, if it said exclusive, all right, then we would just use less than and not less than or equal to. All right, but this is our probability statement. So what we need to find is the probability that x equals 14 through 15, 16, and 17. So we need to find those 4 probabilities. All right, but there is one other thing here. All right, we are no longer talking about the number of customers over a 10-minute interval. Right? We've changed the interval. Right? That means that lambda has to change. Right? Because if we use lambda equals 2.7, right, then we wouldn't be finding the probability that between 14 and 17 customers inclusive, right, came in an hour. Right? We would be looking at the probability that between 14 and 17 customers inclusive, right, came in 10 minutes. Right, so we have to change that. So how do we do that? Right? Sometimes it's very simple. You'll know exactly how to do it. Sometimes it won't be as simple, and you might get a little confused. All right. So if that happens, one thing you can always do is you can say, okay, well, let's set up my initial information. All right. So my initial information I had was 2.7 customers for every 10 minutes. All right, but we don't want it in 10 minutes. We want it in an hour. All right, so we want to get 10 minutes out of there, right, out from underneath, however, that average, right, and we want 1 hour to be there instead. All right, so then we think, well, how many 10-minute periods are in an hour? All right, well, there are 6. All right, so 6 times 10 minutes equals an hour. All right, so then you are essentially going to cancel out the unit of 10 minutes and get 2.7 times 6 customers over 1 hour. So lambda equals 2.7 times 6, or, and I didn't write that down. Okay, that's all right. 2.7 times 6, 16.2. All right, so an average of 16.2 customers every hour. Right, so now we're ready to go. Right, once we've gotten that, right, the rest of it is going to be done just like any of the other ones we've done. Right, you will set them up the exact same, right, except for instead of 2.7, it'll be 16.2, and then it'll be from 14 to 17. Right, really the big thing that I wanted us to get out of this is talking about the fact that you have to change your lambda, right, when you change your interval of time. Right, so we're not going to actually finish this problem. However, I will say that the probability that 14 is less than or equal to x, which is less than or equal to 17, is 0.382. All right, so that way you can try to work that out and see if you're right. All right, so one last thing about the lambdas. Right? A lot of you guys, I'm sure, probably saw that and said, right, this is 10 minutes, that's an hour, we just need to multiply 2.7 by 6. Right, and that's absolutely fine. Right, if you feel confident in doing it that way, that's a perfectly good way to do it. That's the way I would do it normally. Right, but if you are having trouble kind of figuring out what it should be when you change, right, I do recommend setting up something like we did right then, right, so that you can cancel out the old, right, just make sure that you've got the old on top and the new on bottom, right, whatever you're multiplying your original information by, right, and also just make sure you have the right conversion ratio. All right, but this video is getting pretty long and we're at the end, so I'm going to stop talking. That's it for Poisson distribution. That's also it for the this chapter, right, for chapter 6. There's something else I wanted to say, but that's okay. We won't worry about it. All right. Anyway, so that's it for this week, for this chapter and this week. I will see you guys in the next chapter.